All right. Hello, so my name is Catherine, and I'm going to be talking about our paper entitled Why Do Language Models Perform Worse for Morphologically Complex Languages, which is work with Ben Bergen at UC San Diego. So there's an assumption in NLP that given sufficient data, we can use the same training process to train an equally good model for any language. This is a big assumption because we don't have sufficient data for all languages, but given the same amount of data, we see differential performance for different languages. And in this paper, we ask why that is. Specifically, we look at the observed relationship between typology and performance. So inspired by this paper by Gertz et al. In 2018, who observed that there was differential performance across different morphological types. So specifically, fusional languages tended to perform better than agglutinative languages. I'll first explain a little bit about what that means and why this might be happening. So agglutinative languages use different morphemes or different subword chunks to represent each morphosemantic feature. So for example, in Turkish, this word that means fields has three more or less distinct chunks. So in the first one means just field, the second chunk marks that it's plural, and the final one marks accusative case. And these languages differ from fusional languages in that fusional languages use a single morpheme to represent multiple morphosyntactic features in a single chunk. So English is a fusional language. So for a word like R, it can't be decomposed into discrete morphemes, and that one morpheme represents the word be, second person, and plural all together. And so in this paper, we start by replicating this observed effect of performance gap between agglutinative and fusional languages. I won't go into the details now, they're all in the paper, but we tested multilingual and monolingual models, some bigger models up to about 7 billion parameters, and small models. And we used multiple performance metrics, including downstream benchmarks and perplexity. And we found a robust performance gap. So fusional languages were systematically outperforming agglutinative languages. And then in the paper, we outline a couple of proposed reasons why this might be happening. So hypotheses 1 and 2 both have to do with tokenization. In particular, is there something about the way that tokenization interacts with the different internal structure of words between the two types that drives this difference in performance? And the third hypothesis has to do with data set size. So are there cross-linguistic differences such that some languages need more or less data to achieve equal performance? So first I'll talk about the role of tokenization. So in particular, there's an idea that ideal tokenization should be segment words along their morpheme boundaries. So for example, a word like books is composed of the morphemes book and s. And so therefore our optimal tokenization of word books should segment the word along that morpheme boundary. And there's been some evidence that morphologically aligned tokenization improves performance for language models. This might be important because agglutinative languages have more morphemes per word and more unique word forms. And so maybe it's even more important for agglutinative languages to have this optimal morphologically aligned tokenization. And if the tokenization isn't morphologically aligned, then maybe the tokenizers are not representing the structure of the words, and the language models aren't able to construct an efficient representation of the language. And this could be leading to the performance gap. So in the paper, we develop an evaluation for morphologically aligned tokenization for 22 languages based on the universal dependencies and unimorph data sets. And we ask whether agglutinative languages have lower morph score, in which case this could suggest that the morphological alignment may partially explain this performance gap. So for each language, we calculated a morph score, and we found that actually agglutinative languages had higher morph scores than fusional languages. So this does not support hypothesis one, and in fact, it goes in the opposite direction. We looked to see whether some things like oversegmentation might explain these results, but increased segmentation was negatively correlated with morph score and explained very little of the variance. We also looked at the role of tokenization quality. So we used two different metrics, tokens per word to represent compression, but we didn't find any relationship there. And we also used Renyi entropy. We found a very small effect, but it just didn't explain enough of the variance. So we ruled out the role of tokenization in this case, and next we turn to the role of data set size. So as I mentioned at the beginning, just having the same data set size doesn't necessarily lead to equal performance, as previous work has shown. So what are the cross-linguistic differences or considerations that maybe lead to more or less data needed to achieve comparable performance? And specifically, we're asking about maybe the way that the data set size is measured. This is based on our work on where we introduced byte premiums. So we observed that there are a number of bytes needed to represent characters in different writing systems, and that this was leading to different data set sizes based on writing system. So for instance, the sentence, "I like to eat apples and bananas" in English is 30 characters long. Each of those characters only takes 1 byte to represent. So the whole string takes 30 bytes to represent. But in a language like Burmese, there are slightly more characters, but each of those characters needs 3 bytes to be represented. And as a result, Burmese needs 4 times as many bytes to encode the exact same content as English. And looking at data set size, so for a language like Burmese, which in XGLM makes up a very small portion of the training data, we might consider that Burmese has effectively been trained on even less data, maybe as much as 4 or 5 times less data because of these byte premium effects. And so in the paper, we ask whether controlling for byte premium in the pre-training data would remove these performance gap between the agglutinative and fusional languages. And to do that, we use some models that we trained, called them the goldfish models. So we have small GPT-2 models for 350 languages. We have a few different data set sizes for the different for each language. And we trained them exactly in the same way as some other models. The details are in the paper, but we normalized the data set size according to the byte premium. So these are some actual byte premiums for different languages, and what this looks like is for, say, the 100 megabyte pre-training data size, if English got 100 megabytes of data, Spanish has a byte premium of 1.08, then Spanish would be trained on 108 megabytes of data. And so depending on the different languages' byte premiums, their training data would be scaled accordingly. These models are actually available to use in case there's some project that they would be useful for. Yeah, now we can test whether these goldfish models show the same performance gap as the other models we tested. So we used the same analysis as before. The details again are in the paper. And we found no difference in performance between agglutinative languages and fusional languages. So we argue that after accounting for byte premiums, we can explain most of the variance that was previously attributed to morphological type. And therefore, morphological type might not actually be the driver of these performance differences. So returning to our potential causes, we confirm that data set size explains the performance gap, but this isn't necessarily due directly to the morphological type itself. One takeaway from the paper is that it doesn't seem like, in principle, that any language is necessarily easier or harder to learn, at least based on morphological type. But we do still see some unexplained variants, which is important to look into. In particular, I think data quality is a really big issue. So low resource languages often have really low quality data, and agglutinative languages are more likely to be low resource languages. So developing better language identification tools and constructing higher quality data sets might be an important part of understanding how language models might work for different languages. So that's all. You can use MorphScore. It's available on GitHub. As I said, the goldfish models are available on Hugging Face. All the code and data are linked in the paper, and here's a QR code to see the entire paper. Thank you.